Every structure ever built by human hands started with a foundation, not the part anyone photographs, not the part that gets the ribbon cutting. The part that goes in the ground first gets covered up and holds everything else upright for the next 100 years. You don't get to skip this step, and you don't get to assume it. You get it right, or everything above it eventually fails. Stage one of Outbound is that foundation, Earth suborbital, the first rung. And I want to spend some time here because this rung deserves more respect than it typically gets, and because understanding what it takes to do it right is the key to understanding why every stage above it is possible at all. Let's start at the beginning. First principles. Before you build a spacecraft, before you touch a piece of metal or write a line of flight software, you have a problem to solve that is purely physical. You are trying to place a human being alive and functional into an environment that will kill them in seconds without your intervention. No air, temperature swings of hundreds of degrees, radiation, microgravity, and the small matter of getting there and back without destroying the vehicle in the process. Every piece of spacecraft design flows from that problem statement. Your structure has to survive the mechanical violence of launch, the vibration, the acoustic loads, the aerodynamic forces of punching through the atmosphere at speed. Your life support has to maintain a breathable environment, a survivable temperature, and a pressure that keeps human physiology functioning. Your thermal system has to manage the transition from the heat of ascent through the cold of space and back through the heat of reentry. Your guidance and control systems have to keep the vehicle on the right trajectory at every point in the flight. And your abort system, the one you hope to never use, has to be capable of pulling the crew clear of a failing vehicle in milliseconds at any point from the pad to orbit. None of this is simple. All of it has to work simultaneously, and it all has to work on the very first flight that carries a human being. That is the engineering problem of human spaceflight, reduced to its essentials. Everything else is a variation on those themes. Now, how did we learn to solve these puzzles up until today? The honest answer: we learned the hard way over decades with government programs that had essentially unlimited budgets and the full weight of national priority behind them. Mercury, Gemini, Apollo, the Soviet Vostok and Soyuz programs. These were not commercial enterprises. They were geopolitical sprints driven by Cold War competition and funded without much regard for cost. And they produced extraordinary results. In less than a decade, the United States went from Alan Shepard's 15-minute suborbital arc to Neil Armstrong standing on the moon. That is one of the most compressed and remarkable periods of technological development in human history, and it deserves the respect it's earned. But it also produced something else, a model for human spaceflight that was essentially immune to economic logic. Government programs don't have to make money, they have to survive the appropriations process, which is a very different discipline. And what that model gave us in the space shuttle era and beyond was a system so expensive to operate, so politically loaded, so resistant to iteration, that improvements to the human access to space effectively stalled for 30 years. The shuttle flew for 30 years and never got cheaper. The ISS cost somewhere north of $150 billion to build and operate. Both were extraordinary achievements. Neither was a sustainable model for what comes next. What comes next is the commercial model. And the suborbital tier is where you can see most clearly why the difference matters. Blue Origin's New Shepard flew 38 missions over 11 years, carried 92 people to the edge of space, and proved that a fully reusable suborbital vehicle is an operational reality, not a concept. Then in January 2026, Blue Origin parked it, not because it failed, but because the company looked at its own ledger and decided the engineering attention was better spent on orbital and deep space systems. And that's a commercial decision. A government program doesn't make that call. A commercial operator does, because capital allocation is the discipline that keeps the enterprise alive. Virgin Galactic took a different technical path, air launch from a carrier aircraft rather than vertical rocket, and is working toward resuming commercial flights with its new Delta-class vehicle. The addressable market for people willing to pay 6 or 7 figures for a brief trip to the edge of space is not infinite, and that math has caught up with the early operators. The suborbital tourism market is currently recalibrating. That's not a failure of the concept. That's a market finding its actual price point, which is exactly what markets do. Here's what both of those stories tell us. The suborbital tier works as a technology proving ground. It works less well as a standalone business at current price points and cadences. The next generation of suborbital operators will need higher flight rates, lower costs, and a broader customer base, research payloads, point-to-point cargo, crew training, and yes, tourism to build a durable enterprise. And that is precisely what it will get because the demand is real and the technology is mature enough to scale. What does the suborbital tier actually give you as a capability foundation? It gives you reusable vehicles. That's the single most important technology shift in the history of human spaceflight. Every expendable rocket that flew before the reusable era was a system that destroyed itself to do its job. The economics of that are brutal. Reusability changes the cost structure of space access at a fundamental level, not incrementally, but categorically. SpaceX proved it with Falcon 9. Blue Origin proved the concept at suborbital scale with New Shepard. Every program above Stage 1 depends on reusability being a solved problem, and Stage 1 is where you prove it out. It gives you life support systems with real flight hours, crew environments, thermal management, pressure systems, abort systems. All of it gets tested and refined in the suborbital regime before you commit it to the longer missions that LEO and beyond require. The margin for error in a 10-minute suborbital arc is different from the margin for error in a 6-month ISS rotation. You want your systems to have logged time before you stretch the duration. Suborbital flight development gives you a trained workforce. Flight operations, range safety, crew training, mission control. The human systems of spaceflight are just as important as the hardware, and they require repetition to function well. Suborbital programs generate that repetition at lower cost and risk than orbital programs. You build the culture of launch operations at Stage 1. That culture scales upward with you, and it gives you a customer base. The people who fly suborbital today are the early adopters, the ones who are willing to pay a premium to be first, who generate the market data that tells the next generation of operators what the actual demand looks like. Every new industry needs those early customers. Space is no different. Now, here's where Stage 1 extends into Stage 2 and why the handoff matters. The path from suborbital to low Earth orbit is not a small step technically, but it is a logical one. The difference at its core is velocity. A suborbital vehicle goes up and comes back down. An orbital vehicle has to achieve roughly 17,500 miles per hour, enough horizontal velocity that it's effectively falling around the planet rather than falling back to it. That's the physics. And achieving it requires more propellant, more structure, more thermal protection for re-entry, and more precision in every system across the board. But the engineering disciplines are the same ones you developed at Stage 1. The life support philosophy is the same. The reusability imperative is the same. The crew systems, the aboard architecture, the operational culture, all of it carries forward. What changes is the duration and the velocity, and those changes ripple through every subsystem in ways that require more development, more testing, and more operational experience to manage. The commercial LEO station landscape right now reflects exactly that progression. Vast's Haven 1 is targeting launch in early 2027. Axiom Space is planning a 2-module station by 2028, attaching initially to the ISS before transitioning to a free-flying configuration. Starlab, a joint venture between Voyager Technologies and Airbus, is targeting 2029. These are not government programs waiting for appropriations. These are commercial enterprises that have raised capital from investors, gone public in at least one case, and are building toward operations on a schedule driven by market demand and the ISS retirement clock. NASA is targeting ISS deorbit around 2030 to 2031. That date is the forcing function. The commercial stations have to be operational and capable of absorbing the research, manufacturing, and crew operations that the ISS currently handles. NASA's commercial LEO destinations program is structured so that the agency becomes a paying customer rather than the owner and operator, the same model that worked for commercial cargo and crew transportation. Government sets requirements and writes checks. Industry builds and operates. That's the model, and it's the right one. Beyond LEO, the stack extends in exactly the way Stage One predicted. The reusable vehicles that prove themselves suborbital and then orbital become the workhorses for cislunar logistics. The life support systems that accumulated flight hours in LEO get extended for deep space duration. The commercial operators who built their businesses on Earth orbital missions look outward for the next market, because that's what commercial operators do. They follow demand, and the demand for cislunar access is coming. SpaceX's Starship is the clearest current expression of that trajectory. It is a fully reusable heavy lift system designed from the beginning for missions beyond LEO, lunar surface, Mars, and eventually further. It is being built by a commercial company, funded by commercial revenue, and iterated at a pace that no government program has ever matched. The lessons of Stage One, reusability, rapid iteration, cost discipline, are embedded in its design philosophy in ways that the expendable rockets of the government era never were. That matters. It matters enormously, because the stages beyond LEO are not just technically harder, they are economically harder. The time scales are longer, the distances are greater, the margins for failure are thinner. The only way to sustain the effort across those timescales is with a commercial model that generates its own revenue at each stage while funding the development of the next. Stage One makes that possible. It proves out the technology, trains the workforce, builds the market, and establishes the operational culture. It is the base of the pyramid, and the pyramid cannot be built without it. We are, right now, living through the end of Stage One and the beginning of Stage Two. The suborbital market is maturing and recalibrating. The LEO commercial station race is underway. The first generation of truly reusable orbital class vehicles is flying. The workforce that will operate the cislunar tier and beyond is being trained today on missions that are happening now. And this is not theoretical. This is not a roadmap waiting to be executed. It is executing. The foundation is going in. Everything above it is waiting to be built. Let's get to work.